decibels will be 0. And first we want to calculate eigenvalue decomposition of this channel H and channel HA and channel HB. And here, of course, you can see from the structure of these two channels that first channel has rank equal to 1 and second one rank is equal to 2. And we can say that for the first channel we will have only one eigenvalue, and for the second one we'll have two eigenvalues. And in this case, you can see that for channel HA we have one eigenvalue equal to 9. And we can check it with the trace of the channel, but in this case of channel A times channel H Hermitian. And you can see if we sum up all elements in main diagonal, it is 3 plus 3 plus 3, it is equal also to 9. So we have correct eigenvalue value. Then we calculate same thing for channel HB. In this case, we have a little bit complex thing, but in this case, eigenvalues is equal to 6.56 and 2.44. And now let's use these eigenvalues. So we continue this task 1. Maybe I will start in our paper with today's date. So today is the last day of May. So let's write practice 2. May 30. And here maybe also I can add something like continue task 1. So now we can consider point B. And for this point B, we need to calculate first. Of course, we have no channel state information. We have channel state information, but okay, let's first calculate this open loop capacity, or something like channel is unknown to the transmitter. So we'll call it as C open. And we can use equation as follows. So the sum of logarithm base 2 of 1 plus p divided by mt times sigma n squared, p divided by mt sigma n squared, and then we multiply it with our eigenvalues, but in this case with index I, and this I goes for sum from 1 up to R, which means rank of the channel. And of course we can say that this P divided to sigma n squared is our rho, which is equal to SNR in decibels. So for our case, if we assume, let's write for channel 1, so C open with subscript A. In this case, we have the sum from 1 to 1, because we have only one eigenvalue. So I goes from 1 up to 1. Here we have logarithm base 2 1 plus, if we write it using our values, so P is equal to 1. Number of transmit antennas is equal to 3. Then we multiply it with the noise variance, which is equal to 1 also. And then we multiply it with our eigenvalue, equal to 9. So you can see we have here 9 divided by 3 is 3, 3 plus 1 is 4, and we have logarithm base 2 of 4. So let's write it. Logarithm base 2 of 4 is equal to just 2. Yes, but let me check why we here write 1. Eigenvalue. Why we? No, it is for channel A. For channel A, we have lambda 1 equal to 9. But here, somehow we use the square root of 9. But why? Let me check. For example, eigenvalue decomposition. Then we calculate this one. Yes, it's very strange. But let's use 9 because I think it is correct one using 9 here. Yeah, really strange. Then let's assume, of course, we can say that for channel A, we have rank equal to 1. Then P equal to 1 watt. Sigma n squared also equal to 1. Maybe like this. And of course, number of transmit antennas is equal to 3. Then let's calculate the same thing, but for channel B. So C open, channel B. In this case, we will have 2 values because rank is equal to 2, and also we have these 2 eigenvalues. So the sum of logarithm base 2 of 1 plus, maybe let's write it as 1 divided by 3 times with lambda I. And now we'll put these lambdas. So logarithm base 2, 1 plus 1 divided by 3. First one is 6.56. Plus logarithm base 2, 1 plus 1 divided by 3 times 2.44. 2.44. So yes, sometimes maybe you can have something like this in the exam. So you need just write it, for example. So we calculate everything inside of these logarithms. And for the first one, it is logarithm base 2, 3.19. And for the second one, it is logarithm base 2 equal to 1.81. So you can end it as this one on exam, or you can, if you want, change this summation of logarithms with the multiplication inside of a logarithm. So we need to calculate this 3.19 times 1.81. But in this case, I will give you just the answer for this example. So logarithm, hello. So logarithm for 3.19 is equal to 1.67, and for the second one it is 0.86. So it is 2.53. So you can see for the second channel, the open loop capacity is bigger in this case, to this 0.53. And maybe let's write it as before, something like answer for B. So answer for this subtask B. No, in this case, we have knowledge about the channel, but at the receiver, not at the transmitter. And next, in point C, we will consider what if we have this knowledge at the transmitter. And then we need to use some algorithm to calculate this closed loop capacity. So answer for B, let's write C open for channel A equal to 2. And for channel B, so C open subscript B is equal to 2.53. Yes, a little bit in this case. But I think yes, because you can assume it as, for example, you can see that in the for the first channel we have just one logarithm with 1 plus something times overall sum of all eigenvalues. And if we divide it, for example, for 2 eigenvalues equal, in this case we will divide it to 2. What we have, let's assume. So, for example, logarithm base 2, 1 plus 1 divided by 3, and here we multiply with 9 divided by 2, for example. And here we assume logarithm base 2, also 1 plus 1 divided by 3 times 9 divided by 2. So we can change this logarithm as the multiplication of logarithms. So let's first calculate it. Here 3, 1.5, also here 1.5. So we have 2.5 multiplied with 2.5. Logarithm base 2. So 2.5 in square. So it is logarithm base 2, 6.25. Yes, if I remember everything right. Yes, yes, I think 6. Of course, we can check it using calculators. 2.5, 2.5. Yes, 6.25. And you can see in the first case we have logarithm base 2 of 4, and for the second case we have this logarithm base 2 of 6.25. So it is all because of this division to something, and then we sum it up inside of this logarithm. Of course, not sum it up, but multiply it. So yes, if we have bigger number of eigenvalues, we can get this open loop capacity bigger. But here, interesting thing, what if we have information and how this closed loop capacity will be changed if we compare it with open loop capacity. So first, what we can use here, we assume that we have channel state information, so it is water pouring algorithm. So point C here, maybe let's give short notation that, for example, we have channel state information at the transmitter. So in this case, we can use water pouring algorithm. And also I can say, looking to this example, we will have maximization of the capacity if each eigenvalue will be equal to each one. So, for example, if we consider this case, you can see we have 6.56 and 2.44, and we have only increase in 2.53. But if, for example, we assume this case, I'm sure that this value will be bigger. Let me check just because this multiplication is equal to, for example, if we consider logarithm base 2 this thing multiplied by this thing, it is just logarithm of 5.77. So you can see, in this case, we have increasing more than in this case. And also, if you, for example, will have 3 eigenvalues, it is better if each eigenvalue divided by 3 in this case. So 9 divided by 3, and each one is equal to 3. So this case will be the best case for 3 eigenvalues, I can say. So, yes, because it is how work this thing in mathematical form. If we have all eigenvalues equal to each one, we'll have maximum capacity. In this case, for example, open capacity. So first, what we need to calculate. Do you know for water pouring algorithm? If you check your notebooks, so it is, I think, something like lecture number 4. Or maybe 5. No, 4. Oh. Constant mu. Yes, first thing is constant mu. Lecture number 7. I find. So first we say that we set this iteration count to p equal to 1. So we can also use this notation here. Let's assume that, and maybe let's write first for channel HA. So for channel HA, we set this counter p equal to 1. Then we need to calculate the water level or constant mu. So let me write the overall or general equation. So this water level is equal to 1 divided by r minus p minus 1. Then we multiply it with the summation of mt with mt times sigma n squared divided by 2, sigma n squared divided by p, sorry. And then we need to assume the sum of these eigenvalues, but 1 divided by eigenvalue. So the sum
1 divided by lambda I, where I goes from 1 up to this R minus P minus 1. R minus P minus 1. So let's use this equation to calculate water level for channel HA. In this case, we can write mu is equal to 1 divided the rank of this channel is equal to 1. So 1 minus 1 minus 1, so it is just 0 here. Then number of transmit antennas is equal to 3 plus 3 times 1 divided by 1, so it is just 3. And then we multiply it with only one eigenvalue, so 1 divided by 9. In this case, we have 1 divided by 3. No, not 1. Here we have 3. Then we multiply this one by 3, so it is 9 divided by 3, so it is 10 divided by 3. This thing is the first step. Then we need to calculate the power allocation using this water level. In this case, we can say that omega will be equal to only one value because we have this rank equal to 1. And maybe also I will give you general equation first. So omega I, this power allocation vector, is water level minus number of transmit antennas multiplied by the noise variance, and this thing is divided by transmit power multiplied with this eigenvalue. And then we can say that our omega I is equal just to omega, and this one is equal to 9 divided by 3 minus number of transmitted antennas 3 times 1 divided to 1 times 9. And you can see we have just 9 divided by 3 or 3, because here we have 3 in the denominator. So this thing is the last thing for this water pouring algorithm. So next we can say, of course, we need to check to the negative values, but we have only one real value and positive value equal to 3. So next, maybe I will use another page. Let's calculate the same thing, but for channel B. So this thing, how we can in which direction or using which antenna we should transmit, because you can see in this case we have only rank 1 of a channel, so we can say that we have only one good path and 2 very bad paths. And in this case we will transmit only by the first path, and it is something like if you also check next thing in lectures, you can see that we next use this how we say this matrix, something like scaling matrix, which is capital D, matrix of capital D, and it is equal just to the diagonal matrix of these omegas. So omega 1, omega 2, etc., omega r. And of course, it is optimal, optimal, and optimal. And we can say also in this case that this one omega optimum is equal to this omega and equal to 3, of course. And next, we will use this d as scaling matrix before the transmission of data, because you can see that the last thing in the transmitted signal is these transmitted symbols. In this case, it is vector. We multiply first with this precoding and with this scaling, but we scale it by the square root of this matrix or by the square root of these values and our original data. So in this case, yes, it is something like just, how to say it, dominant eigen mode transmission. But of course, we have only this one eigenmode. So next, let's consider. Yes, this one.
If you have, for example, another number more than this.
Yes, we will have it for the channel B, so we can.
No, I mean,
how
we can decide this, which channel.
So we decide by our butter pouring algorithm. So we need just how to say it. So we iteratively calculate these omegas, and we need to switch off these negative values. And you can see, maybe I need to check. Do I have butter pouring with switching off? I'm not sure. So maybe I will try to prepare you how this algorithm works. And you just switch off one, and this all power will go to, for example, if you have rank equal to 3, equal to 4, maybe. And you see that omega 1, omega 2, and omega 3, for example, bigger than 0, and omega 4 is less than 0. And maybe, for example, let's say that this overall omega is equal to, okay, 4. So if we have, so overall this omega, let's call it as omega sum, for example, is equal to 4. The number of, so the rank and the number of data streams, for example, that we have 4. And first, let's assume that all these values bigger than 0. So we will have this summation of lambda 1, lambda 2, lambda 3, and lambda 4 is equal to 4, like this one. It is, for example, A. But if, for example, example B, lambda 1, lambda 2, lambda 3 bigger than 0, and lambda 4 is less than 0, then we switch off this, the last data stream, and recalculate everything, and get another lambda 1, lambda 2, and lambda 4, and we lambda 3, and this lambda 4 is equal to 0 in this case. And we need to check, do we have negative values in this lambda 1, lambda 2, lambda 3 updated one? And for example, if all these values bigger than 4, I can say that the summation of this lambda will be equal to 4. Because I think also have something here.
the summation of these lambdas should be equal to number of transmit antennas, as I remember. So because it is just how we can work with this number of antennas. Yes, in the for this channel HA. No. We transmit only using first antenna in this case, because here, for example, if we calculate this D, it is equal to 3, 0, and 0, like this one. But of course, we assume only the first one because we have rank is equal to 1. Through one, in this case, yes, through one data stream. So let's continue with channel B, and maybe I will open the window. So for channel B, in this case, we increase rank up to 2. Oops, sorry. So this one, for example. Let's write for channel H subscript B. For H subscript B. So first, as before, we set the number of the iteration equal to 1. So let's write P is equal to 1. And let's use general formula without this the repetition of this general formula here. So we can say that this mu is equal to, maybe I will show it like this one. So first we write 1 divided by the rank. Rank is equal to 2 minus 1 minus 1 here. Then number of transmit antennas is equal to 3 plus 3 multiplied with noise variance and divided to transmit power. And here we need to multiply to the sum of these eigenvalues. So first it is 1 by 6.56. And second one is 1 divided by 2.44. It is something like 0.15. So it is 0.15. And if we calculate 1 divided by 2.44, it is 0.41. And then we need to multiply to 3. So if we multiply it, we'll have 8. Sum everything.
it is 4.68, and then we divide it to 2. So we have 34. This thing is equal to 2.34. Then we to find our optimum power allocation. So maybe let me show here. So I is equal to water level minus number of transmit antennas times variance divided by value. In this case, omega 1 is equal to 2.34 minus 3 times 1 divided by 1 times 6.56. So you remember that 6.56 is equal to 0.15. So it is 0.45. In this case, we have 1.59 here. 5 and let me check. Yes, something like 1. 3 times 1 divided by 1 times 2.44. So this thing is 0.41. If we multiply it by 3, it is 1.23. 1 here and 1. So in this case, it is a little bit less than number of transmit antennas. So we have this water level is equal to 2.34. Or yes, sum is equal to 3. Yeah, great. And in this case, you can see that if we sum this, first, of course, we need to check the sign of these values. So it is first positive, second positive. We can end our butter pouring algorithm. And here, let's say that we have the answer for this subtask C. So for channel E, we have omega 1, or just, okay, let's write omega 1 opt, which is equal to 3. And for channel HB, we have first omega 1 opt is equal to 1.89, and omega 2 opt is equal to 1.11. And next subtask is calculating the closed loop capacity using this omega, this power allocation vector. So put this one here. Let's write this point D here, subtask D, and maybe let's write closed loop capacity. Closed loop capacity.
So let's assume first channel A.
So for channel H subscript A,
And now we will use this
notation as C closed.
and of course we substitute. And maybe first I will give you the general equation for this closed loop capacity.
So C closed is equal to the sum which goes from I equal to 1 up to R. And here we have logarithm base 2. One plus the same thing, P divided by MT times sigma squared, but here we have this power allocation value, omega I. So P times omega I divided by MT times sigma n squared, and then multiply it by our eigenvalue.
And in this case, if we calculate closed loop capacity for channel A,
it is equal to logarithm base 2, 1 plus this power 1 multiplied by omega 1 opt, which is 3, then divided by the number of transmit antennas 3 times 1, and then multiplied by 9. Yes, by 9. So in this case, we have logarithm base 2
of 10, yes. And maybe we can leave it as this one. If we compare the value with open loop capacity, for open loop capacity,
it is equal to logarithm base 2 of 4. Then, of course, let's assume second channel, channel B. So C closed subscript B is equal to the sum of the logarithms. So first logarithm, it is 1 plus these values. Here, yeah, these values. So 1 multiplied by 1.89 divided by 3 times 1. And here, the first eigenvalue, it is 6.56. Then we sum it up with logarithm base 2. So 1 plus 1 times 1.11 divided by 3 times 1 and multiplied by 2.44, second eigenvalue. So what we have here.
so if we divide 6.56 by 3, it is equal to 2.19.
So this one, 2.19. We should multiply these two things here.
And if we divide these things, it is equal to
0.81.
But of course, let's, for these examples, use calculators. So first thing, oh, yes, but I think I will try to prepare the tasks to have easier multiplications and divisions, maybe, because it is hard to calculate by hand. Of course, it is something like 5 minutes of calculation, but of course you can make some typo, and in this case the answer will be wrong. So if we use calculators for these tasks, first one, it is 5.14, I think, approximately. And second logarithm, it is 1.11 multiplied by 0.81 plus 1. So it is something like 1.9. Maybe let's do it as before, logarithm base 2 of 4.14. So. Or we can do it here, of course, using computer. I'm not sure, so we should check it. Base 2, 5.14. So or maybe we should use Google for it. Yes. Okay, let's do it. So it is logarithm base 2 of, like this one, yes? Oh, sorry. Like this one. Oh, yes, maybe. Okay, let's calculate this thing as before for first example. So it is something like logarithm base 2 of 9.6. So it is something like 3.29. 3.29. So it is a little bit bigger than for yes, and if we compare it with open loop capacity, it is 2.53. So you can see that we also improve our capacity value using yes, for if we use open loop capacity, for example, if we have no information at the transmitter, the capacity is equal to 2.53, and we have and information at the transmitter, it is equal to 3.29.
Канал А лучше, да?
No, I think
Там лог 2.10. Б лог 2.9.
yes, if we consider
Но там раз.
if we consider, I think it is all because of this dominant eigenmode transmission. So if we find this thing in our lectures, as I remember, we use dominant eigenmode transmission when we know channel state information. So yes, channel is known to transmitter Mimo case. And this thing, something like when we want to extract special diversity. So yes, in this case, only one eigenvalue is better if we compare it like this one. So we can say, for example, how to say it? If, for example, rank is equal to 1, it is, for example, channel A, and for channel B, rank is bigger than 1. So two cases. And if we compare, for example, open loop A and open loop B, it is better to have more eigenvalues. So we can say that this thing bigger or equal. So C open of B is bigger or equal to C open of A. But if we, yes, calculate closed loop capacity for channel A and closed loop capacity for channel B, it is better to have one eigenvalue in this case. So we can say that this thing is bigger or equal to 1. Yes, it is very interesting information from these two cases. So maybe and calculate what is logarithm of 10. So it is something like 3.32. Something like 3.32. So how much time we have? Approximately 25 minutes, yes? So what else I can give you here? Something short. Or to start some, in our case, maybe let's start one more case for open loop capacity and closed loop capacity, but using, you can have something like this on exam. So for example, you are given some Mimo channel, and we assume, for example, flat fading. Let's maybe write task 2 here. Task number 2. So you given a Mimo channel, given Mimo channel with flat fading. And for example, it is channel of size 4 times 3. 4 times 3. And sometimes you are also given the singular value decomposition of this channel. So for example, singular value decomposition of this channel, H U times sigma times V Hermitian. Also, you are given with these values of U and V and sigma, but in this case, I will give you only this sigma matrix here. So this sigma matrix is equal to first value, it is square root of 2, 0, 0. Second value, it is 1, 0. And third value is also 1. So from this sigma matrix, you can say the rank of a channel, of course. And for example, first subtask can be compute the open loop capacity. So how you can calculate this open loop capacity in this case for this task? Can you say, do you have some ideas how to do it? So we already know this general formula. So of course, you should use this formula for open loop capacity. But how we can do it using this sigma matrix? So compute the open loop capacity. And for example, the signal to noise ratio, so P divided by sigma n squared is equal to 0.5 dB. So first, of course, we can write this C open in general case. So C open is equal to the sum of I equal to 1 by R logarithm base 2, then 1 plus, let's write here rho divided by empty lambda I. So what should you do first? Some ideas? No? Okay. So first you can see that we have only singular value decomposition. But usually when we calculate open loop capacity, we use this eigenvalue. And then we can say, oh, we know this connection between singular value decomposition and eigenvalue decomposition. And also we know the connection between eigenvalues and singular values. So these eigenvalues, it is just the square of singular values. In this case, we'll have this matrix of 2 times 1 times 1. for eigenvalues. And then we can calculate this open loop capacity. So C open is equal to logarithm base 2, 1 plus maybe 1 divided by 2 So what is the number of transmitted nodes? I think you can say it. No. We assume it as MRMT. Yes, of course. And the first value is 2. And maybe we can say that this thing is 1 divided by 6. Yes. So the second one is 1 plus 1 divided by 6 times 1. And the last thing is 1 plus 1 divided by 6 times 1. And yes, of course, as before, we need to leave it using logarithm, I think. So this thing is 2 of 6. Overall, it is 8 by 6. This one, and this one, like this one also. So it is the summation or multiplication of logarithm base 2, and here inside 8 divided by 6 times 6, 7 divided by 6 times 7 divided by 6. So this one is for open loop capacity. And then second thing, subtask B is what is the optimal power distribution. If, for example, we say that signal to noise ratio goes to infinity or goes to minus infinity. So, second subtask, what is the optimal power distribution? Power distribution. Across these 3 eigenmodes. То, что здесь было? Across the 3 eigenmodes. And here, first assumption that signal to noise ratio is plus infinity or goes to plus infinity. And second case, when signal to noise ratio goes to minus infinity. So for SNR goes to plus infinity, and SNR goes to minus infinity. Two extreme cases. And of course, here you should remember this water level equation for water pouring. So you can see here we talk about optimal power distribution. So we can say that we know the channel state information at the transmitter. And in this case, we use this water pouring algorithm. No, so this one. So this first eigenmode, second eigenmode, and third eigenmode. Yes, it is eigenvalues, but when we talk about the data streams, we say it as eigenmodes. So first, let's assume this water level mu. Maybe water level mu. So let's assume this mu, which is equal to 1 divided by r minus p minus 1. Then here we write mt plus mt. We can say we divide it by rho. So yes, we need to see this thing here with these assumptions. R minus P minus 1. So first, let's see what we have in water level. So in this case, we need to think about these things, something like logical solution. So what if first, for example, rho goes to plus infinity? From this thing, we can say that 1 divided by rho goes to 0. Because this thing goes to infinity. So 1 divided by infinity, it is just 0. And in this case, we can say that this part is equal to 0. Because we divide empty by this infinity simultaneous equation. And in this case, our power allocation is just empty. If we, for example, assume P equal to 1, but not empty, but empty divided by R. Then we should think about the power allocation. So the main thing here is omega I is equal to mu minus mt divided also by this rho times our eigenvalues. In this case, we also use the same thing. So rho tends to plus infinity. In this case, 1 divided by rho tends to 0. This thing also goes to 0. And in this case, our power allocation is just mt divided by rho. So we use equal power allocation in this case. You can see that we divide overall power allocation equal to mt by this number of eigenmodes. In this case, it is equal to mt divided by 3. And this mt is equal to 3 also. So 3 divided by 3 equal to 1. So our power allocation scheme is 1, 1, and 1. Yes, and let's try to get this thing, because it is a little bit harder in this case, because if rho tends to minus infinity, in this case 1 divided by rho tends to, let me see, something like not to infinity in this case, but yes, it's yes, yes. Yes, equally. So we use all eigenmodes. So in this case, we will have this maximum capacity in this high SNR case. But now we need to assume this low SNR case. Let me check what we have to do here. So in this case, we should analyze the sign of these eigenvalues. Let me show you how we can do it for this case. So first one was for signal to noise ratio goes to plus infinity. And let's write here, and maybe this one is the last thing for today, that our signal to noise ratio goes to minus infinity. Here we will use power allocation equation first, and we use it in interesting form. Okay. So here we assume the overall power allocation as the sum of these values here. But why? Okay. It is linked a little bit strange for me what they do here. So we put this here. No, we use. Okay, I got it. I got this thing here. So they write. So first they write omega I. So for equation with mu minus mt times, in this case we write it as rho times lambda I, and then they change this mu using general formula for this water level. So they write it as 1 divided by R, then mt plus mt divided by this signal to noise ratio, and here we assume this summation from I equal to 1 to R, 1 divided by lambda I, and then minus mt divided by signal to noise ratio times eigenvalue. Then they open these braces.
So what we have in this case? We have MT divided by R. Then okay, maybe I will show you by step. So MT divided by rho times R times this summation of 1 divided by eigenvalue minus MT rho divided by lambda I. Then we want to create new braces using this MT and this MT divided by rho. So it is first one MT divided by the rank, then plus MT divided by signal to noise ratio. And here inside of the braces we have 1 divided by R, sum of all eigenvalues minus 1 divided by eigenvalue. And yes, here we need to remember about this given singular value decomposition and what we calculate in the subtask A. So we have these eigenvalues, which is equal to 2, 1, and 1. And next, we need to use this information and analyze the sign of this thing. So first calculate this part, 1 divided by R, and times this thing here, the summation. So 1 divided by R, sum, I can say that it goes from, yes, okay, let's write it in general case first. And for our case, it is 1 divided by 3, and then the sum. So 1 divided by 2 plus 1 divided by 1 plus 1 divided by 1. And it is equal to 5 divided by 6. It is all because our rank is equal to 3 and our eigenvalue matrix is 2, 1, and 1. So next we need to calculate power allocation for each eigenvalue. So power allocation for the first, it is something like this 5 divided by 6, this part, minus this part. So 5 divided by 6 minus, in this case, first one, 1 divided by 2. So it is something like 1.3. Yes, but if we assume the multiplication of this one with our signal to noise ratio, which goes to minus infinity, we can say that this thing is multiplied by infinity. Then if we assume second and third case, it will be 5 divided by 6 minus 1 divided by 1. And you can see in this case we have negative value, 1 divided by 6 multiplied by this infinity value, and also minus 1 divided by 6 times infinity value. And you can see we turn off these two things, so switch it off, and we can say that our power allocation scheme in this case is
matrix of D, which is equal to 3, 0, and 0. And you can say that if we have high SNR regime, we use equal distribution to each antenna. And if our signal to noise ratio is very low or goes to -infinity, we will use only one eigenmode. So yes, that's all for today. And for this task 2, we have also 3 subtasks. It is water pouring algorithm, then how we can compute the closed loop capacity, and how we can choose recoding and decoding things. And the last thing here, after which critical signal to noise ratio, we will turn on these 2 streams. So you will need also calculate some interesting things using like logical value of the SNR. And maybe we will do it tomorrow. Yes. Yes, that's all for today. If you have some questions, of course, you can ask me. And yes, thank you for today. That was very good practice. So do you have another lectures here? Oh,
Yeah.
okay. So I will leave.